Okay, so just a quick recap of what we are doing, where we discussed at length those transformations, projections and scheduling last time. Just a quick recap. What we had was that that in an n-dimensional DG, if suppose we had edges like this, nodes and edges, this was IN, this was JN, and this was KN, this was edges, and we map it to a lower dimensional DG of m dimensions, dimension m. So IM, JM and KM like that. Then basically this is a mapping function. JM was FJN and this was FKN. Then we said that if this mapping function is linear, then it offers some advantage. That is, FJN you can write as F. What is Jn after all? Jn is In plus this edge vector in an n-dimensional coordinate system. This is that edge vector In plus. So, this is nothing but In plus En, and if it is linear, it will be f of In, which is Im, plus f of En. So, this f of En if I know, I can also find out f of Kn, because f of Kn is what? F of Jn plus Fen, because the edge is same. So, that means what will be important is only to find out the mapping of the respective edges, and DG is defined by a few edges only. Those edges keep getting repeated. Okay. In a DG, n-dimensional DG, all the interior coordinate points are filled up with dots, that is processing nodes, but how they are connected? So, there are a few basic edge vectors, they go on connecting the nodes and they keep repeating, right. So, if I know those, if there is map of those edges, then I can draw the entire DG in the lower dimension. That is what I said. Then I made a statement, and unnecessarily there was a problem in proving that last time, and I was going perfectly okay last time, but I don't know why I got confused. I made a statement that if you are transforming Rm, if f is such that you are transforming an n length vector to m length vector, that is you are transforming R into Rm. In fact, it should be Z, because R is set of real number which includes our fractions also, isn't it? But here we are dealing with only integer numbers, but permit me, because this is a general result. So, I am using the general framework of real numbers, and if it is a length n vector, then we are in Rn, and if f is mapped, if it is a mapping from Rn to Rm, then we said, I made a statement, if f is linear, then f can be represented always by a matrix of dimension m cross n. It will multiply the given vector from Rn, give you the map in Rn. That is what I said. Then there are some goof up in that proofs. I thought that okay, let's start with the linear function, but I said that I will give a proof. In fact, the proof was perfectly okay last time. I mean, unnecessarily there was a confusion. So, that part I will complete, but taking that result again. So, this f was equivalent to one matrix. I think I used the notation T, no? Did I use the matrix T? T m cross n. I will drop this index m cross n very soon, because it occupies some space. So, it was working on Rn, any vector from Rn, and giving you the corresponding length m vector. Then I said that we will design this this matrix m cross n. Obviously, m is less than n, such that there is one m cross n square matrix which is full rank. Okay. There is one, this is m cross n. So, there is one m cross n m matrix which is full rank, which is all linearly independent columns and linearly independent rows therefore. Okay. If that be, and then there are other columns, it could be this matrix, or it could be some other matrix, or it could be some other, mind you. It is not that this is fixed. You could choose this to be a square m cross m, or some other m cross m square matrix also is possible. In this case, this matrix has rank m. This is general result we said. Then we considered this kind of equations Tx, I drop this index m cross n, Tx equal to 0, and many non-zero solutions of x are possible. I said that these non-zero solutions, you find out x1, x2 like that, which are also linearly independent. So, the space spanned by them, you will get a finite number of such solutions only, which are linearly independent. Say you get odd number of solutions, x1, x2, dot 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 xr, which are linearly independent. So, the space spanned by them means set of all linear combinations of those basis vectors. Each of them qualifies for a solution here, because T working on that, linear combination will be 0. And if I add to any coordinate vector a linear combination like this, result does not change, because f after all f is denoted by T, T working with that part will be 0. That means many nodes in the original space map to same node in the lower dimensional space. That is what I said. Then I said that I will consider a particular case where it is not m cross n, because there is too general. For your sake, I will consider only transformation from n dimension to n minus 1. If you want to go further down, go on repeating the transformation, though ideally we not do that way, but just for your sake I said n to n minus 1 dimension. In that case, that is T, okay. In that case, we design it such that there is one submatrix of the size square and the one column left. In that case, I showed, and I will not prove it again, that null space means solution space for this kind of equations. They consist of only one vector and its all the scalar multiples. Okay, we proved that. So, there we took a basic vector which I call D. Basic vector means, of course, it will have integer values, and integer values shows that, I mean, its norm, that is, if you take the square and sum, square of each will be sum, there is a minimum possible. Okay. Of course, avoid the trivial solution of x all 0, that will be ridiculous. Do not bring, okay, I am looking for minimum norm solution, so do not think that you can put x to be all 0, then we do not get anything, isn't it? So, forget that trivial solution. Out of all other solutions where you have got integer values, take the one which has minimum norm square. I give it a name D. So, that means, what are the solutions for this equation? D or integral multiples, because I am interested only integer coordinates, integer valued vectors. So, that means D, 2D, 3D, minus D, minus 2D, minus 3D, like that, all integral multiples of D. The D was given a name projection vector. So, to any coordinate vector here, if I add D or 2D or 3D or 4D or whatever, I will always get the same thing. That means, processors which are located at a gap of D vector contains direction, mind you. D is not only some coordinate, D vector, when you show this vector in this n dimensional plane, it is pointing in some direction, right. So, it is showing a direction, also distance, it is a vector. So, processors which are separated by D vector, they all map to the same point. That is what we came to last time. So far so good. Parallelly, I was doing scheduling also. Scheduling is each point in the, here in the DG there is one implicit time axis, but after transformation time axis will go. Maybe that is how it becomes n minus 1. N dimension consists of one particular axis which is the time axis. Now I want to throw it away, because in real IC design you cannot have one direction as time axis, isn't it? So, I want to throw it away. So, it becomes n minus 1 that way. I mean, you can view it that way. Okay. So, but when IN is, this node is mapped to 1 and another node is mapped to 1, I know their dependence relation, that IN has to be completed, then only JN can take place. Output of IN has to go to JN, right. So, that dependence relation must be maintained in the lower dimension also, that is schedule. If I give a time schedule for this IN, that should precede the schedule for JN. Remember, for the time being, I am assuming processor computation time to be 0. Otherwise, schedule of this plus the computation time together, that time should precede the schedule of this. That I will come to, I will generalize all those things later. For the time being, assume processor time to be 0. So, schedule of this should be before schedule of this, okay, and but schedule is a scalar. That is another thing. Schedule cannot be a vector, schedule is a time instant, scalar. Then again, schedule can be a function S working on IN, giving a scalar number, which is schedule for this, S working on JN, giving a schedule for this node, okay, which is a scalar number. Then again, I said that I will have advantage if S is linear, because then in that case, S of JN will be simply schedule of this plus S of En, and this will be S of Jn plus S of En. So, if I know S of En, then I am through. So, S of En will be what? You understand, the same thing, same linear advantage of linearity. So, we assume S to be linear function. In that case, all schedules can be described by simply finding out the S function of the basic edges. Okay, if this is, I mean, this is edge En, then S of En will be the time gap between the schedule here and schedule here. Okay. So, I just need to find out the S function of existing edges, those basic edges, fundamental edges, that is all. Okay, that is the advantage. But then S is now is a linear function, and S is taking En, that is n dimensional vector, but giving a scalar, because S is a time, after all it gives you only time constant, time it is not a vector. So, capital M is in that case 1. So, it is 1 to this matrix will be 1 cross n, which is a row vector. Okay. which is a row vector. So, row vector times each coordinate vector will give a time. Only thing is, as I said that two things are important there. These are all pre-cap, but these things, they are fundamental things are you are not used to this kind of thing. I am repeating quite at that length. On choice of pace, there are two constraints so far. What is one constraint? Schedule of this must not take place before the schedule of this, which means what is the schedule of this? Schedule of this plus S, I mean S of En, isn't it? So, S of En must be greater than or equal to 0. In fact, I would want S of En to be at least 1 or higher, 2, 3, 4, so that means there will be a delay. A delay will introduce, reduce the critical path, but at least it should be greater than or equal to 0. And secondly, if you consider processors which are separated by D, 2D, 3D, 4D like that, which are all to be mapped on 1, their schedules must not clash. So, processor here and then another one situated, there may not be edge, another one is situated with a gap, this vector is a D, this is not an edge, D came from the null space, processor situated at a gap of D, I mean separated by vector D, they all map to the same node. So, this and this, suppose they are separated by vector D, this is not an edge is here, okay. These two and any one down this line, upward or downward, okay, they all will map to gap here, that means their schedule must not clash. So, that means what is the schedule of this? Schedule of this plus S of D. So, that means S of D must not be 0, otherwise the two schedules will clash, this is another constraint. And S was a row vector. Now, did I call it S or S transpose? S transpose, because then I made also a statement that I am more familiar with column vectors. So, when I write S function in the matrix vectors notation, then let me write S as column vector. Though actually here it, as it shows that it's the way it will operate on the coordinate vector, it will be a 1 cross n, but I will write it as n cross 1, call it S, and then when I operate I will make it S transpose. So, it will again become row vector. That means S transpose NEE, drop this, must be greater than or equal to 0 all for all valid edges, and S transpose D must not be equal to 0. These are constraint on choice of S. I now give you one more definition here, which I didn't do, and then I will go back to that proof. This quantity S transpose D, what does it indicate? That okay, two processors which are separated by D vector, they are mapped to the same guy. Okay, this fellow, it is working for this guy also, isn't it? But it is not working for them in the same time. There is a time gap. How much is the time gap? S transpose D. If that S transpose D is less and less, then it is a better utilization of the resources. Idle time is less, isn't it? If on the other hand, I give schedules here, I choose S such that S transpose D for this and S transpose D for they are quite apart. So, that means this node is properly utilized. Okay. And mind you, S, all these deal with integers, S, P, it is not any real number. So, you understand this? So, that means S transpose D is what? It is a time gap between what? The execution time by this node for this processor and by this node again for this processor, the gap between them. If that gap is less, that means I am utilizing this in more efficient way. So, there is something called hardware utilization efficiency, HUE, hardware utilization efficiency, which is measured as by the take the mod, because S transpose D could be negative also, H could be the indirect S transpose D, take the mod. Okay. So, lesser it is, better it is. This is one thing. Now, before I move further with these definitions and take up a particular DG and show you various possible, choose S, P arbitrarily and then give you some arrays and explain their functions, let me come back to that proof, which I left halfway, and in fact, I was doing perfectly fine that day, but unnecessarily we got confused. It was just I saw something else, because I wrote something and saw something else, I invited a confusion for me. Anyway, before I go into that proof, you tell me one thing, how do you do matrix into vector multiplication? Let me see your knowledge. How do you do? Given a matrix, this is a matrix. A11, A12 dot dot say A1n, AM1 dot 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 AMN, and there is a vector x1 dot 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 xn. Normally, I mean, how do you do matrix multiplication? This way, A11 x1 plus A12 this and this, isn't it? Again for this row. Now, you know, I mean, you have reached a stage where you should forget this. You should never do that way, especially if you are a student of our department. You should view this as column 1 vector, right? This is E2 vector, this is En vector. Then my claim is this is same as x1 times this column. Please verify. Please check that both way you get the same result. Please check. Easily, E1 top is A11, so A11 x11, E2 top is A12. For those who are not understanding, E2 top is A12, A12 times x2, and then En top is A1n, A110 times xn. They all get added. So this right hand side is a vector, but the top guy is this to this. Is that understood? Similarly, second guy, third guy, like that. Okay. Advantage is that you then directly see the output as a linear combination of the column vectors. As the column vectors are spanning a space, you are roaming in that space, you are finding out a particular linear combination of these column vectors. Combiner coefficients are given by the given vector. Okay. Always view matrix multiplication. Actually, this is the matrix vector multiplication. It is just linearly combining the columns by some coefficients put in a vector form. Okay. Now I come back to that proof. Such things should have been taught in your maths. I mean, you do that matrix vector multiplication in school. These days it comes to school, I find, for early stage, but now no longer. Okay. Now that day I said that suppose, in fact, you know, there's a very trivial thing. Again, I apologize for getting confused. There is no scope of any confusion. If this was taking you from R what? Rn to Rn. That means for all vector for any x belonging to Rn, what was f of x? Okay, f of x. Now, point is any vector x, I was going like this, I define some basis vectors, trivial, it is called trivial basis vectors, 1 0 0 0, E2 0 1 0, you get up to n. Okay, this is called trivial basis. Then any vector x, I can write simply as xi ei, isn't it? Any vector x, top component is x1, x1 into e1, so it becomes x1, others are 0. Then next guy is x2, x2 into e2. So this guy gets multiplied by x2, x2 into 1, x2, dot dot dot. Last guy is xn, en, xn, en. Only this gets multiplied, others are 0. And then you add, you get back your original vector, isn't it? This is called trivial basis. So you linearly combine this trivial basis by the coefficients of the vector, you get back your original vector. The vector representation actually representation in trivial basis. This is called trivial basis. Any vector that I give you, column vector, that's a representation of some abstract quantity called vector using in a trivial basis form, using trivial basis, linearly combining the trivial basis vectors by the given coefficients, you get back your vector, right? F of x, so if I simply write x as in this form, and it is linear, and what is FEI? FEI is actually map of this in the m-dimensional space. So, it is basically a m cross 1 vector. Yeah, this is basically m cross 1 vector. I was doing perfectly fine that time, map of this Fe1, map of this Fe2, dot dot dot, map of this Fen, and you are multiplying by the coefficients and adding. That is your map, and I am assuming linearity. This I can simply write as this form. Write and check. What I am doing is simply, I am considering, please understand little bit of matrix here. For that reason only I am doing it, otherwise I could have skipped this. When you do this map and all, what I am actually doing? I am finding out when you do this mapping, my claim is you hit upon the trivial basis. If you want to get this matrix representation, hit upon the trivial basis. Take f of this, call it Fe1. Take f of this, call Fe2. Now, if those vectors you put side by side, you get a matrix of size m cross n. E1 map is Fe1. Put there is a column vector of length m, first vector. E2 map is Fe2. Again a column vector of length m. So, there is second column. Dot 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 Fen last column. So, you get a matrix. Now, my claim is this is simple, na? This quantity is nothing but what? I told you just beforehand how do you do matrix vector multiplication. You linearly combine the columns by the coefficients. That is what you do here. Instead of writing in the summation form, I am writing in matrix vector multiplication form. Isn't it? This column times x1, this column times x2, dot dot dot, this column times xn, all get added. So, original vector remains here, and this is my t. So, how to construct t? Very simple. You give me the map function. I do not have to apply map on everybody to get its complete definition. I simply hit upon, choose the trivial basis, consider map of this, dot dot dot, map of this. Resulting map vectors I put side by side, form a vector, form a matrix. That is all. That working on your given vector will give you the map. All right. So, you just going fine that time. I don't know, I just got confused somewhere. So, I come back to now examples of systolic array. Okay. Again, we start with the 2D FIR filter. I am telling you, it is just doing for exercise, because they are really, you don't get anything by systolizing. Whatever you get, you can directly write. You can directly derive them using your common sense. But for a practice, for getting experience, that is enough. And then we move to another some other examples. Okay. So, I come back to that 2D DG for a FIR filter, which I think we have taken up quite a few times in this course so far. That is given now, this I will be drawing quickly. Please do not ask me to explain, because this you know. What it is, you know. I will not also draw the processor here anymore. You know what is that processor. We have taken it up many times. And output is found out from n equal to 1 onwards. So, till n equal to 0, it was at rest. Okay. These are n axis 1, 2, 3, 4 like that. This is getting somewhat clumsy. I go to the next page. Let me take longer gap, this is coming too close, it becomes to congest it. This is n axis. Huh? Okay. I am not describing the processors. There is a particular reason why I chose this color arrangement or not, which I know is in my mind. It's not that I used colors just for decoration, which you cannot do on your thing, because you don't have color pens. Okay. I will consider two examples assuming the time permits. This DG, processors we all know. This DG is given by 3 edges. This DG is given by 3 edges. What are those 3 edges? One is in this direction, you see. What are the fundamental edges? This is in this direction, one edge is going in this direction, another is going up, right. One edge, you can say weight, filter weight, that is B0, B1, B2. This is what? What is this edge? This is weight edge is going in this direction. Say x axis, y axis. Okay. This two dimensional world. So n into 1 vector means 2 into 1 vector. This direction. So 1, this is it's not going in this direction. Another is input. Input is just reverse. Input is going up. 0, 1. Another is this direction, result. Not 1. 1 minus 1. Downward. If you assume origin anywhere, any node to be origin, it's going this direction, isn't it? 1 minus 1. Bas, that's the these 3 edges defined. So as a first example, there is no specific choice, or there may be other considerations which you are not considering here. You start with P. Okay. P was what? Not P. I think, did I say P or T? T. In the last class, I said P. No, T was the matrix, right? So, throughout the class today I used T, what did you tell me to change it to P? I do not remember. So, it was P then, na? So, I make the correction, whatever I am doing for T, I mean whenever I say T here, that was actually, I mean I used the notation P in the last class for that, okay. Well, I did not remember that I was using the notation P, you see, but I should, but normally no, to operator we are so familiar with using the notation T, capital T for operator, I just carried that thing. So, actually what I did for T today, actually this T here stands for capital P that was used last time, okay. So, suppose we take P to be, and here P will be what size? M cross N, M is 1, I will be mapping to a one dimensional array, 2 dimension to 1 dimension. So, M equal to 1 to N equal to 2, M cross N, so it is actually a row vector. But still instead of calling it P transpose, let me call it P, unnecessarily again you will be confused. When it becomes more than 1, it will be a matrix. Okay. So, P, you understand P will be 1 cross 2. P, there are plenty of choices. For this example, P is 0, 1. P is 0, 1. Okay, there is a submatrix of size 1 cross 1 which is full rank, so no problem. This is P 0, 1. What is the meaning of, before I go into S vector and find out D vector, what is the meaning of P 0, 1? P will work on any 2 dimensional vector, give you the resulting coordinate. That means P times a coordinate vector, any coordinate vector here, say I comma j. I comma j, you understand? I 1, 2, 3 like that, j 1, 2, 3. This is 1, 1. This is 0, 0. I comma j, both I and j are integers. I in this direction, j in this direction, say typically. So, P I comma j is nothing but what? J. P is 0, 1. Okay, so it is j. What does it mean? It means that in I comma j, only j comes up. I has no role. So, that means if j is fixed, suppose j equal to 1, I varies along this line. J equal to 1, I1, I2, I3, I4, but j equal to 1. So, means all these fellows will be mapped to only one fellow, that is j, and j equal to 1 in this case. So, in a 1D array may be shown in a vertical direction, j equal to 1, that point, that node will correspond to all the nodes here. That means even from this you can tell me what will be D vector. What is D vector? D vector is such that processors separated by D vector are mapped to the same guy. These processors, they are mapped to the same guy. Even from here you should be able to say what is D. What is the separation? 1, 0. So, this should be 1, 0. From there, here also you can see, but that is by inspection. Mathematically, P 0, 1, P is what size? Please see, please do not talk. Physically you have explained that you are seeing all these nodes getting mapped into the same node. Okay. And therefore, there it so happen that in this case there is an edge also. Don't view this, don't see these edges. Whether there is an edge linking them or not is not important. These fellows, they all get mapped to jth processor. So, what is the separation vector between them? 1, 0. So, D should be 1, 0, that is comes from physical arguments. Mathematically also P 0, 1, 1 cross 2 is a size, out of which there is one matrix of size 1 cross 1, which is null space. After all, we will have same thing, na? I mean, we will have dimension 1, only as before n into n. I mean, I was dealing with the general case of n minus 1 cross n vector, choosing the matrix n minus 1 cross n matrix, choosing the matrix so that there is a n minus 1 cross n minus 1 square submatrix like 1 cross 1 square submatrix. That time I said that null space, that is if you form an equation like P x equal to 0, all solutions of the equation which form a solution space, that will be integral multiplied by basic solution, that will apply here also. Only thing is n has taken a specific value 2, m has taken a specific value 1, that was n minus 1 cross n, it is 1 cross 2, n is 2. Okay. What is that basic vector? You do not have to solve in this case, you really do not have to solve an equation. If this physical argument does not come to your mind, if you cannot view this, even just looking at this vector, you can find out D. What is D after all? D is such that P D equal to 0. I am solving that kind of equation, P x equal to 0 and finding out the solution space, and D is taking to be 1, which is non-zero, but which has minimum, norm, integers, but with minimum norm. So, D is 1, so P D is 0. So, P in this case 0 1 row vector length 2. So, what should be D? Forget about all these things. In a 2D world, you have got one vector. You have to find another one which is orthogonal to this. Is it orthogonal to this? You know all this, I suppose, orthogonal to this. So, if it is 0 1, then it is 1 0, and that is what we are getting here. For this FIR filter, things are very easy. When it is 3 dimension, say 3 to 1 dimension, that time you need to do some maths. Here, if it is 1 0 1, I can say this by 1 0, so that they are orthogonal. If they are orthogonal, P in D equal to 0, and only one such D is possible. Others are just multiples of D that have already proved in the general case. Okay, so just using orthogonality find out the D, that satisfies the equation P into D equal to 0. There you choose D so that all the coefficients are minimum integers, so that norm square is minimum, and then by the general theory we know all solutions of this kind of equation will be an integral multiple of that. We are taking integral multiple of that basic D. So, D is obvious. D in this case is 1 0. I am taking here transposing now, wherever possible. Here I did not, because P here is a vector, but in a general case a matrix. But D is always a vector, S is always a vector, D is always a vector, and when I deal with vector I prefer column vector, that is why I made it column. So, I will be using D transpose that way. P in this case turns out to be a vector, but in general a matrix. That is why I am not putting a transpose and making it column vector, all that. Okay. But here I know D will always be a vector, so better keep it a column vector. S is always a vector. S for this problem, S should be chosen such that S transpose D is not equal to 0 firstly, and then S transpose times each of the edges must be greater than equal to 0. That I am coming later. For the time being, you choose S. This one example, S they are taking to be 1 0. First you see S transpose D, D is a column vector now, is 1. S transpose is a row vector 1 0, D is a column vector 1 0, 1 into 1, so 1. So, at least that is satisfied that S transpose D equal to 1, which is non-zero. Okay. Now, we form this table of H transformation. H and then P times H and S times. Okay. What I am doing? I told you that location wise, when I map n dimension to n minus 1 dimension dg, I have to only bother about the edges, how the edges get transformed. So, I will write all the edges here. Okay. PE, PU no 0 1, now the routine exercise PE, this will become what? 0, 0 1, 0 into 1, 1 into 0, you know PE, P of P times this H, see this is a very routine thing, then P times this H, this is 1, 0 1, 0 1, okay, and P times this H, what is that? Minus 1 I suppose, no? 0 1, so 0 1 you bring here, minus 1, S transpose E, S transpose that is 1 0, 1 1 1. So, that means this H, weight H will have a delay. Okay. Weight H, I will come to this meaning of this 0. First we do this routine exercise, S transpose E. So, S transpose input will be, input is what? 0 1, S transpose is 1 0. 0, you are right, very right, and here 1, fine. 2 dimension to 1 dimension. In general, I have found out a vector here I comma j, x axis I, y axis j, then maps to j, right. That also shows, that also takes care of one problem, that all the infinite number of processors here, they get mapped to one guy, all the infinite number of processors map to one guy, and all the infinite number of processors map to one guy. So, even if the DG is infinitely long, my resulting DG now after mapping in the lower dimension is not infinitely long. But I will consider another example where that problem will come up. It will be better DG, better transformation, but then that infinitely long thing will come up, and again we have to use some clever manipulation of things, reuse of the DG and all those, that I will come to. Okay, so that infinity problem is taken care of. Okay, I am trying to give you this kind of, I mean, just example. By this example, I am going to kind of, I am trying to give you some taste of the things. Okay. So, j, I comma j, this goes to j, and normally j is y axis, that is why I am drawing one dimensional line only. After 2 dimension to 1 dimension, so it will be one dimensional thing, but instead of x axis I am drawing y, because it was after all going to j, and j normally is reserved for y and I for. So, this is a j axis. In the j axis, suppose this is j equal to 1. So, all these guys will map to, okay, suppose this is j equal to 1, this axis I have to consider, this is j equal to 1, all these nodes will be mapped here, all these nodes will be mapped say here j equal to 2, and all these nodes will be mapped here. Now, edges in this direction, like say consider anyone along this line, anyone along this line, this there was an edge. What was that edge? Input. Okay. That edge gets mapped to 1. 1 means in one dimension 1, that means unit vector in that length, in that direction. That means this edge will come up like this. Are you getting me? Look at this edge. What is this edge? This edge is the input edge. That was getting mapped to 1. 1 means what? I have got only one dimension now. There 1 means in the positive direction unit vector. So, the positive direction unit vector. So, but along this line, the schedule is 0. That means what? No delay along these lines. No delay along these lines. So, I am not putting any delay. Then comes weight. Weights are going in these directions. One weight like this, one weight like this, one, and all these nodes are mapped into 1. Physically, you can see if all these weights are mapped into 1, then weight will remain there only, it cannot go anywhere. This particular weight will remain there, that is why it is coming 0. That means, but there is a delay. So, that means I have to have a path here which starts from here and goes, but does not go in this direction. Because of the delay, I have to do a rounding thing. And last one is result. It is coming in the negative direction with one delay. Physically, what is happening now? This array, let us try to understand this array, but this is just a, you see, when you do this, is basically diagram to diagram mapping. Forget about all VLSI, everything. It was a plot, it is an array of points, I mapped it like this. Okay. But then I have to now use my engineering intuition to understand what is happening, and then if something is required, then we will do. But it is just a transformation of one figure to another figure. Okay. Please.
Weights, sir, like what do you mean by the same weight going in a delay, sir?
No, I am only repeating, I will come to that. There is it will finally I will just keep it as a fixed weight. That is why I said it is a diagram to diagram. I am just routing transformation following this table. This is not the final diagram. Final physically meaningful diagram will come after this, which is nothing but a transpose form of a FIR filter. Okay, that will come, but I am trying to explain it to, step by step. Okay, what is happening? Xn is coming here. And what is this weight? After all, the weights correspond to this line, that was B0. This weight was B0. This weight correspond to this line, this was B1, and this weight is B2. What is happening is, this is input and B0, and you remember that processor, what the original processor was doing. That time I was showing the edges in a particular direction. What it was doing? It was taking B weight input and X input multiplying the two and adding to the result input and giving the new result, isn't it? This time also this is the result input. To that it will add this B0 times this X, and this will come out as a new result. Similarly, in the same cycle Xn moves here. What is doing is, there is no delay in this path. So, Xn times B0 here plus whatever was coming, that comes out in this path. Xn moves here. I will draw a further circuit using flip flop and multiplier and all that using that time, but just understand here first, because this is a pretty simple one. Next one will be complicated. B1 is here. So, B1 times the same Xn plus whatever was coming, that is put down this line, that will come here in the next cycle, and again Xn times B2 plus, if something was held up here as that, otherwise 0, I am showing this, otherwise 0, that will put down the line. In the next cycle Xn plus 1, the same B0, this shows that B0 is held, and again in the next cycle when new data comes, again that will be multiplied with the same B0 plus the new output that is coming from this side, they will be added and new output will be generated like that. Okay, this is the physical meaning of this, but practically I will never do like that, that when the same data, same weight is circulating, I still reserve a flip flop. Now, practically what I will be doing, now again I draw it horizontally. There is one line for input, that dot, that processor I am putting in a box like this. What does the processor have? It multiplies this input and the weight, adds to whatever is coming down the result line. Result line is this line. That within this, it will be multiplying this with what? If you do perfect, like this, then there will be a delay, and then you have to put the coefficient B0, it will multiply, again circulate. But do I really need this arrangement? I don't. Just use a fixed multiplier B0, use it in every cycle. When you are treating B0 as an age and all that as a signal, then you have to. When you are treating B0 as a kind of signal, as we have assumed in this, then you have to hold the signal by a delay and all. But actually B0 in this case, since it is repeating, you can hold it like this, make it a fixed coefficient multiplier. Okay, so I am showing, but actually it is B0, so I am not. And this result will get added to whatever was coming. Whatever is coming, this path has a delay, but this guy will go to the next, no delay in this path. Okay. Next one. Here if something comes, otherwise 0 initial condition, as in the DG. You can add more stages. This is nothing but transpose FIR filter. Xn, whether you give this direction or give this, as long as there is no delay, they are all correspond to same line. Okay. the xn into b0, xn into b1, there is a delay. So, what comes out is xn into b1 into xn minus 1, xn into b2, 2 delay. So, what comes out here is b2 into xn minus 2, they all get added. With this you get the normalifier filter output. This is transversifier filter, no big deal about it. Okay. That is why this example I took up just to give a practice. We do not need to go through all that to derive a transversifier filter. Even other arrays also you can derive directly, but I am giving a practice of various transformations and all, so that I can take up higher dimensional case. Like I will be after some time doing matrix into matrix multiplication, okay, 2 by 2 into 2 by 2 matrix, and then you have to do a DG. It could be 3 by 3 also, any n by n into n by n. You have to draw the DG for it, and suppose matrices are coming one after another in time. So, this DG you have to operate in real time, you have to systolize that. It will be a 3D DG. You can either map it to 1D or 2D, again various choices of P, D, S are possible. We will consider some there. Okay. Is it okay? Yes.
Is it always the case that the weight coefficient?
No. This has got a particular name. They have given a name, broadcast input, move weight. No, this is weight stay. Broadcast inputs, move results, weights stay. This input is broadcast, weights stay, and move result. Move means when I say move result, through a delay, not broadcast. Okay. But there I can choose also. In the next example you will see weights will circulate. Okay. It all depends on how you choose P and also your S. On D you do not have much choice, because P D has to be orthogonal. So, once you choose a P in this case, D automatically follows. But P and S can be chosen. P can be chosen most independently. You get a D. S to some extent independently, but again S has some constraint. S transpose D must not be equal to 0, and like here also you have found out. I did not do the cross checking, but you see none of them, everybody, all of them are greater than equal to 0. This is a must. Okay. This is a very simple example. In the next class, I will consider a little more complicated example, where that infinite nature of that DG will be coming in, but by clever manipulation, we will have a final circuit which is only which will have a finite number of stages, not infinite. In this case, all the nodes along this were mapped into 1, so thereby you needed 1 here, 1 here, 1 here, 3. Okay, if you just reverse it, if you suppose consider P matrix such that these 3 processors map into 1, these 3 processors map into 1, these 3 processors map into 1, then as long as this DG continues, you also continue. But do not worry, there again after a while you can stop and you can use whatever you have, you can use the philosophy of reusing. Okay, you do not have to go on doing it. That kind of one such example I will take up, which is slightly more complicated in the next class. Okay, thank you very much.